Let's read this question. The two slits in the Young's double slit experiment are separated by a distance of 0.03, which means small d is what is given. The first sum I'm doing it. Small d is equal to 0.03 millimeter into 10 to the power minus 3 meter. Okay, an interference pattern produces, okay, on the screen which is kept 1.5 meter away, capital D has been given. The fourth bright fringe is at a distance of 10 centimeter. The distance of the fourth bright fringe, the position of the bright fringe is n into lambda into capital D by small d, which is the fourth. This is the formula for the bright fringe position. So it's 4 into lambda into capital D by small d itself is equal to 10 centimeter, which is 10 into 10 to the power minus 2 meters from the central maxima. So find the value of lambda. So you just have to substitute what is 4. You don't know lambda, you know d, which is 1.5, you know small d, which is 0.03 into 10 to the power minus 3 is equal to 10 into 10 to the power minus 2, with which you can find what is lambda. So you just have to cross multiply this and bring this, it's 6. Okay, so then it's 10 into 10 to the power minus 2 into 0.03 into 10 to the power minus 3 by 1.5 into 4 is 6. So this is how this itself is 10 to the power minus 5. So it's this is 10, which is going to become 10 to the power minus 4 into 0.03. Can we write this as 3 into 10 to the power minus 2 by 6? So the 3 2s are 6. 1 by 2 is 0.5 into 10 to the power minus 6, which is 0.5 into 10 to the power minus 6, which will be 5 into 10 to the power minus 7. Supposing I'm going to multiplying and dividing by 10, so it will be 5 into 10 to the power minus 7. And supposing I'm making it multiplying dividing by 1000, so in that case it will be 5000 into 10 to the power minus 10, therefore it's 5000 Armstrong. So that answers the first question. So let's go to second question. In Young's double slit experiment, the fringes are measured with a micrometer eyepiece 80 centimeter behind the double slit. Young's double slit experiment, fringes are measured with a micrometer eyepiece, okay, behind the slit. It is found that 20 of them occupy the distance of 10.92 millimeter. Find the distance between the two slits. Okay, let me answer this question for you. So now continuing with the sum, in Young's double slit experiment, fringes are measured with a micrometer eyepiece 80 centimeter, which means the capital D is 80 centimeter. The capital D is 80 centimeter. There are 20 of them are found at a distance of 10.92. If 20 of them are found at a distance of 10.92, okay, so you can divide the 10.92 divided by 20 so that you get the fringe width, because there are 20 fringes are found at a distance of 10.92 and the number of fringes is 20. Take the whole distance divided by 20, you get the fringe width of each one. So this will be 10.92 by 20, and that is in millimeter, because they have given it in millimeters. So this is 20 millimeter. So then you have to convert that into meters. So you write 10.92 by 20 into 10 to the power minus 3, because that millimeter can be now converted into meters by multiplying with 10 to the power minus 3. So that will give you the fringe width. Once you find the fringe width, what is the question now? Find the distance between the two slits. Small d is what they are asking. So you know that beta itself is lambda into capital D by small d. So small d is equal to lambda into capital D by beta. So what is lambda? Is it 5460 Armstrong? So 10 to the power minus 10 into capital D. Capital D is nothing but 80 centimeter, which is 0.8 meters. Okay, by beta, which is 10.92. 10.92. This value can be substituted by 20. 10.92 by 20. So then that 20 will go to the top. 20 will go to the top. So it's the 10 to the power minus 3 has to go to the top because 10.92 millimeter. So 10.92 10 to the power minus 3. So 10.92 10 to the power minus 3 and by 20. So that beta has been substituted here. So you calculate this value. If you calculate this value, you'll get 0.7912 into 10 to the power minus 4 meter. So that's the value that we get. What is the answer that they have given? So the 0.8 millimeter. 0.8 millimeter. Okay. 10 to the power minus 4. 0.7912 into 10 to the power minus 4 meter. How is it? If it's minus 3 meters, at least I can write it as 0.8 millimeter. How is minus 4 becoming? I don't understand that. But this is the calculated value. You can check out your answer. Okay, so let's go to next question. The next question is the third question. The two slits 0.2 millimeter apart. So small d is given to be 0.2 millimeter. Produces an interference pattern on the screen at a distance of capital D is equal to 80 centimeter. What is the distance? The third bright fringe. The distance of third bright fringe is y is equal to 3 into lambda into capital D by small d. That's the distance of the third bright fringe, and where the wavelength itself has been given. So it's 3 into 5890 into 10 to the power minus 10 into capital D, which is 80 into 10 to the power minus 2 by small d, which is 0.2 into 10 to the power minus 3. Just calculate and see if you're getting that answer that they have specified there. Okay, sorry, just hold on guys, just hold on. So you can just find the value, whatever the value is will be the distance of the third bright fringe. Second dark fringe, when it's a dark fringe, you all know it's 2n minus 1 into lambda into capital D by small d is the position of the 2n by 2. 2n minus 1 by 2 into lambda into capital D by small d is the position of the second dark fringe. So it's substitute n as 2. 2 to the 4 because second dark fringe, this is bright fringe formula. Okay, n into lambda into capital D by small d is bright fringe formula. So 2 to the 4, 4 minus 1, 3 by 2 into lambda into capital D by small d. So then it's, if you had calculated this value, you just can divide it by 2. That's all. That will give you the that value. Okay, so I wish I had calculated that. I'll tell you the value of this turns out to be, according to the answer, 7.068 millimeter. So a half of it, therefore I won't even calculate 3.534 millimeter. Half of it, which is obvious, no? Because this 3 into lambda is 3 by 2 into lambda into capital D by small d. So it makes sense. So I would do that. And the next thing is the distance between the third dark and the seventh bright fringe. The third dark means third dark minus the seventh bright fringe. Okay. So y7 bright minus third dark, the distance between them. So bright fringe means 7 into lambda into capital D by small d, minus dark fringe means 2n minus 1 by 2. 2n minus 1 by 2 means in the place n you put 3. 3 to 6, 6 minus 1, 5 by 2 into lambda into capital D by small d. So then you already know what is lambda into capital D by small d. Okay, it's easier to calculate if you take lambda into capital D by small d out from here, 7 minus 5 by 2. So lambda into capital D by small d is 14 minus 5, which is 9 by 2, which is 4.5. You just want to find the value of lambda into capital D by small d alone. Can you see from here? I'm teaching you a shortcut. You can divide your answer, this answer that you got here, by 3. So if you do that, it's 3 2s are 6, 10, 3 3s are 9, 16, 5 3s are 15, 6 3s are 18. So this will be the value of lambda into capital D by small d, 2.356. So you can write this as 2.356 into 4.5, or into keep it as 9 by 2, it's even more easier. 2 ones are 2, 2 ones are 2, 7 twos are 14, 8 twos are 16, and 9 eights are 72, 9 sevens are 63, so 70, 9 ones are 9, 7 twos are 14, 15, 16, 9 ones are 9, 10. Oh wow! So look at the way you can calculate, such shortcuts are available to get the answer. So that completes the third question. So let's go to next question, which is the fourth question. I hope I'm recording. Yeah, it is getting recorded. Fourth question. The width of the slit S1, S2 in M's double slit, when the ratio S1 and S2 are in the ratio 4:1, S1 and S2 are in the ratio 4:1, how will the intensities of the maxima and the minima in the interference pattern related to? Okay, you should know that the intensity is directly proportional to slit width. Okay, intensity is directly, let me do the sum, intensity is directly proportional to slit width. So according to me, the I1 by I2 will also be in the ratio 4:1. In the, how will the intensities of the maxima and minima in the interference pattern related to maxima and minima? Okay, let me think. Okay, so let's continue. You know that I1, the incoming intensities, I1 by I2, these are the incoming intensities, itself is the ratio 4:1. I1 by I2 is equal to 4:1. So I1 is equal to 4 times I2. And you know how to calculate the resultant intensity. You know R maximum is A plus B the whole square, and R minimum is equal to A minus B the whole square. R maximum is root of A plus B the whole square, and this is root of A minus B the whole square, and intensity is square of the amplitude, so you can, it will be A, or in other words A plus B and A minus B will get squared. So the maximum intensities formula is A plus B the whole square, and minimum intensities formula is A minus B the whole square, and where A and B are the initial intensities, and intensity is square of amplitude, so this is nothing but A square by B square. Therefore A by B itself is 2:1. So considering that, okay, they're asking you for the ratio of maximum and minimum intensity. What will be the intensities of maximum? Yeah, ratios only. So it's A plus B the whole square by A minus B the whole square, and you know A by B's value, so take B square out from here. A by B plus 1. By B square out, A by B minus 1. A by B itself is 2. 2 plus 1 by 2 minus 1. The whole square and a whole square. Okay, so then therefore B square get cancelled. So 3 by 1. So 9:1. So that is your answer. So this is the slits and the intensities of the incoming intensities will be in the same ratio. With that, you put it in the formula of I max by I minimum, and you get this 9:1. So let's go to next question. So which is the sixth question. The sixth question, in Young's double slit experiment, the separation between the slits small d is equal to 0.002 meters, 0.002 meter. Okay, the distance of the screen from the slit is 2.5. Capital D itself is 2.5 meter. The light of wavelength lambda, which ranges from 2000 to 8000 Armstrong, is allowed to fall on the slit. Find the lambda in the visible region. Find the lambda in the visible region that will be present on the screen at 0.001 meter from the central maxima, some position y. Okay, of the central maxima. Also find the lambda that will be present at a point on the screen in the infrared as well as ultraviolet region. In Young's double slit, separation between the slit and the 0.02 meter. The distance between the screens is 2.5 meter. Lambda is ranging from 2000 to 8000 is allowed to fall on the slits. Find the lambda in the visible region that will be present on the screen at 0.00. So your position has been given. You know capital D, small d. You can find out what will be the wavelength pertaining to that region. So you know that y is equal to lambda into capital D by small d. Lambda into capital D by small d. So then if you put that itself 0.001, which is 1 into 10 to the power minus 3 is equal to lambda into capital D is 2.5 by small d is 0.002. So when we calculate, you can get one lambda. Let's see what it is. This itself is 10 to the power minus 3 is equal to lambda into 2.5 by 2 into 10 to the power minus 3. So this will become 1.25. So a lambda will become 1 by 1.25 into 10 to the power minus 6, which will be nothing but 1000 by 125. 100 by 125. So let's cancel this with 5 2s are 10, 5 2s are 10, 5 5 is 25, 5 4s are 25. So it's 0.8 into 10 to the power minus 6. So that is the wavelength that I'm getting here, 0.8 into the, supposing I want to make it as Armstrong, so then I multiply with 10 to the power minus 4, which means I'm multiplying dividing by 10 to the power 4. Okay, so then it becomes 8000 Armstrong. So that is the value I'm getting. Find the lambda in the visible region that will produce, that will be present on the screen at 0.01 from the central maxima. Also find the lambda that will be present at the point in the infrared as an ultraviolet region. Okay. What is that answer, that 4000 Armstrong? I'm not getting that. That's the issue. Okay, unless I've made any mistake. Slit is 2.5. Yeah, the distance between the screen, the light of wavelength ranging from 2000 to 8000 Armstrong. So it's allowed to fall, and find the lambda in the visible region. Lambda in the visible region that will be present on the screen. I'm just trying to manipulate this question, okay, and get the answer. I got 8000 Armstrong, which apparently is the second part, okay. So you know that there will be a visible region. There will be a visible region, and there will be infrared and an ultraviolet region, one above and below it. So then therefore you can't call it as, you can't put n is equal to 1 here. You put n is equal to 1 here and got this answer. So it's got, this has got to be, you have to put n is equal to 2. So when you put n is equal to 2, when you put n is equal to 2, there will be an additional 2 here. Okay, and final answer will get divided by 2, and you'll end up getting a 4000 Armstrong. We'll end up getting 4000 Armstrong. Okay, that should be for the visible region, because one above and one below will give you infrared and ultraviolet. So you can now put n is equal to 1. And now you put n is equal to 1, which will be 8000 Armstrong, which will be for the region above, and n is equal to 3. So then that will be, so you put n is equal to 2 and get it for visible region. So basically moral of story is put n is equal to 2 and get it for the visible region, and put n is equal to 1, which means divide the answer by 2, you get infrared, and you divide the answer by 3, you get ultraviolet. Because it's n is equal to 2 stands for the visible region, n is equal to 1 stands for infrared, and n is equal to 3 stands for ultraviolet. So then that's 8000 by 3. So then therefore it's infrared region is 4000 and ultraviolet region is 8000 by 3 Armstrong. So that's clear. Also find the lambda that will be present at a point on the screen in the infrared as well as ultraviolet region. Also find the wavelength that will be present on the screen in the infrared and ultraviolet region. Okay. We got it, na? That's what it is. Whatever we got, 8000 by 3. Oh, find the value that will be present at a point on the screen in the in both in infrared and ultraviolet region. Find the lambda that will be present both in infrared and ultraviolet region. Let me think. And regarding the last part, I don't know. Okay, the 2000 Armstrong, find the wavelength that will be present in both infrared and ultraviolet. That's something let's discuss in class and figure that out. Okay, then you can WhatsApp me and I can explain to you. Let's discuss that in class. Let's go to 7th question. In Young's double slit experiment, the distance between the phone call 1 second. Sorry guys. So the Young's double slit experiment, distance between the slits small d is equal to 2 into 10 to the power minus 3 millimeter. Okay, millimeter has been converted. What would be the width of the each slit so as to obtain 10 maxima of the two slit interference pattern within the central maximum of the single slit diffraction? Okay, the central maxima, supposing this is the central maxima, say keep it like this, the central maxima, where the slit width is 2 millimeters, what should be the width of the slit, each slit? So as to obtain 10 millimeter, then the distance between the slits is 2 millimeters. What should be the width of each slit so that obtain 10 maxima? So there has to be 10 maxima here of the two slit interference pattern within the central maximum. Okay, so then, okay, let's do this. So this is a very, very difficult sum. We need to kind of learn this properly. So you know the position for supposing there are 10 maximas, let's say 10 into lambda into capital D by small d. 10 into lambda into capital D by small d, and that will be 10 times beta. There are 10 maximas, 10 fringes are there. Okay, so then corresponding the angular separation. Supposing the angular separation, okay, you know that the angular separation will be this, is the angular separation theta is equal to y by capital D, or in this case we are going to call it as x or y, I don't know whether you want to call this position as x, which covers the 10 maximas. So then therefore theta 1 itself is x by capital D, which itself is 10 into lambda into capital D by small d by capital D. So 10 into lambda by small d. So this is what you get as to be theta 1. Now the angular width of the central maxima in the diffraction pattern. The angular width is given by theta 2 is equal to 2 lambda by a. You know, angular width, you know, d sine theta is equal to n lambda. D sine theta is equal to n lambda. And here this has been called as a and this has been called as theta. And it's 2 lambda. It's 2 lambda because its width of the central maxima is double it. So it's 1 into lambda. Okay, so then you know that d sine theta is equal to 1 lambda stands for the first minima's position in diffraction. Okay, so you have to double it because it's about the width of the central maxima. So this is, we can call it as theta. This we can call it as a small a, that's what they are calling it here, diffraction. So it's 1 into lambda. So theta is equal to lambda by a, but that is only for the central maxima. This is a position y1 on the either side and there's a point p1 as a point p2. We are talking about this distance. Okay, that's the position of the first minima. And so the another minima here, so double it you get. So in diffraction, you know, 2 into lambda by a. 2 into lambda by a stands for your angular width, which is theta 2. So you should know that in interference, it says theta 1 is equal to x by d, theta 1, and theta 2, which is the angular width, will be of the central maxima is 2 into lambda by a. Okay, so then as theta 2 is equal to theta 1. Oh, here comes the part where I'm getting very confused. How did I get this? For the first equation, theta 1 is equal to x by d. X by d in an interference pattern corresponding to, let A be the width of the slit, linear separation between 10 bright fringes. The 10 bright fringes. Okay, where are the 10 bright fringes? Is it above the central maxima? What should be the width of each slit so as to obtain 10 maximas of the two slit interference pattern within the central maxima? So within the central maxima, I'm getting 10 bright fringes, which shows that there are 10 into lambda into capital D by small d would be the distance, the total distance itself. Okay, the total distance. And how are they calling that as, they calling that as angular separation. This theta 1 is not a mere theta which is y by d, it is this spread. This is what they are calling it as theta 1. Okay, now you must be clear. So then theta 1 is equal to obviously the entire position, which is 10 into lambda into capital D by small d, which is about the central maxima, yes, which is also equal to x by d. Theta 2 is the width of the central maxima, which is 2 into lambda by a. So since theta 1 is equal to theta 2, it's 2 lambda by a is equal to 10 into lambda by small d. Okay, 2 lambda by a, but therefore you have to lambda and lambda get cancelled, so you get 1 by a is equal to 5 by d. Therefore you get a ratio that d by a is equal to 5, d is equal to 5a. So a stands for diffractions width, that is the slit width, whereas d stands for small d is the slit width, and therefore a is equal to d by 5. A is equal to d by 5. So the d itself is 1.00 by 5 millimeter, which eventually gets you to 0.2 millimeter. D by 5, D is 1 millimeter or 2 millimeters here, D is 2 millimeters. Sorry, it's 2 by 5. So then therefore it's 0.4 millimeter. Very difficult sum. It's a very difficult sum for me. Let's try to understand this question again. The distance between small d has been given in an Young's double slit experiment. The distance between small d, this is small d for an Young's double slit experiment. What would be the width of the slit so as to obtain 10 maximas of two slit interference pattern with its central maxima of single slit diffraction? Obtain 10 maximas of the single slit interference pattern with a central maxima of single slit diffraction. What question is this? I don't understand. All I understood is, supposing there is a central maxima and you're going to have 10 different if you're going to have 10 different maximas in the place of in the place where there's a central maxima situated, where would central maxima be situated? That will be situated in diffraction pattern. In diffraction you will have a central maxima. In interference you will have in that you can divide it into slits so that you can have almost 10 maximas. So you're comparing an interference pattern and a diffraction pattern, and you're trying to find an angular separation which is theta 1 in an interference and a theta 2 in a diffraction. Theta 1 is equal to the space occupied by the 10 maximas, which is 10 into lambda into capital D by small d, that the whole distance by capital D. Okay, that is what is theta 1, which is the angular separation, and for theta 2, which is for diffraction, it's theta 2 refers to the width, what attributes to the central maxima, so it's 2 into lambda by a. So theta 1 is equal to theta 2. I hope you understand. It's very difficult, but anyway, if they ask you this is the way you have to do. It's difficult for me too. If you want, I'll explain the class. In Young's double slit experiment, the distance between the plane of the slit and the screen, capital D, is 1.5 meter. What would be the distance between the slit if the bandwidth, small d is what they are asking, if the bandwidth means beta is 1 millimeter, which is 10 to the power minus 3 meters, and lambda itself is 6000 Armstrong. What should be the bandwidth itself? Again, bandwidth formula is lambda into capital D by small d. So this itself is 10 to the power minus 3 is equal to lambda itself is 6000 into 10 to the power minus 10 into 1.5 by small d. So small d is equal to 6000, 15 6 are 90, right? 90, so it will become 9. 15 6 are 90, 000, 1 of the decimal get cancelled, into 10 to the power minus 9, 10 to the power minus 10 by 10 to the power minus 3. Minus 3 goes up, it will become 9000 into 10 to the power minus 7. So then take the 9 into 10 to the power minus 4, or 0.9 into 10 to the power minus 3, so 0.9 meters, so it becomes millimeter. That's the very simple sum. The sum that I found it hard is that sum where there are 10 maximas present in one central maxima produced by the single slit diffraction. So a single slit diffraction produces one central maxima in which there are 10 maximas that can be produced by Young's double slit. What should be the small d relationship between small d and small a is the question. I found it very, very hard, that question. So let's go to 9th question. A beam of light consisting of a wavelength 6500 Armstrong. This is lambda 1 and lambda 2 is 5200 Armstrong, are used to obtain interference fringes in Young's double slit experiment. The distance between the slit small d is given to be 2 into 10 to the power minus 3 meters. The distance between the slit and the screen is capital D is equal to 120 centimeter. Find the third bright fringe on the screen from the central maxima for 6500 Armstrong. So for 6500 Armstrong, you have to find the third bright fringe. It's only interference. So 3 into lambda into capital D by small d will be the position of the third bright fringe. Find the third bright fringe, central maxima, where the bright fringes are due to both coincide. The bright fringe, okay, third bright fringe on the screen from the central maxima for 6000, where the bright fringe due to both are coinciding. Okay. So if both the bright fringes are coinciding due to this wavelength and this wavelength, you know that it's a lambda 1 into capital D by small d, capital D, lambda into capital D by small d is the position of the third, some mth bright fringe, I don't know, and an nth bright fringe, formed by lambda 2 into capital D by small d, they both are coinciding. So this is the position of the mth bright fringe, this is the position of the nth bright fringe using different wavelengths. They both are coinciding, means capital D small d will get cancelled. So m by n itself is lambda 2 by lambda 1. Lambda 2 is 5200 by 6500. So you know 13 3s are 52, 13 5s are 65, 13 4s are, so 4 by 5. So m is to n is in the ratio 4 is to 5, means fourth fringe, bright fringe, and the fifth bright fringe, or this wavelength lambda of 6500 and this wavelength of 5200 are coinciding. The fourth bright fringe of that and the fifth bright fringe of this. Okay. So therefore you found that m is equal to 4. That is enough. If with m is equal to 4, once you know m is equal to 4, you can substitute so what is the question? Find the third bright fringe on the screen from central maxima for 6400 Armstrong, where the bright fringe due to both wavelength coinciding. Bright fringe due to both, I don't understand the third bright fringe. That is not okay, because n is equal to 4. I got it because I assumed m and n, he is assumed. So you know that the fourth fringe and the fifth fringe, one of the fourth fringe, one wavelength of the fourth fringe, and the fifth m is equal to 4 and n is equal to 5, or what is coinciding. That much I understood. So I have to substitute m is equal to 4, and I don't understand the third bright fringe, because according to me it's a fourth bright fringe and the fifth bright fringe of this wavelength and that wavelength is what is coinciding. Okay, let me find out the position of the fourth bright fringe, 4 into lambda into capital D by small d, where I should put lambda, which is which belongs to which wavelength? 6500. So it's 4 into 6500 into capital D itself is 120 into 10 to the power minus 2. Armstrong means 10 to the power minus 10 by small d is 2 into 10 to the power minus 3. So when you substitute this, you will get one value of y. That will be the distance for whether the mth fringe or nth fringe, it will be coinciding. So y will be the same. So it's, let me try to do this. This and 2 will get cancelled. So you get a 2 into 6500 into 10 to the power minus 10 and minus 12 it will become. And you still have a 120 by 10 to the power minus 3. This goes up, it will become 10 to the power minus 9. Then you have another 10 from here, which makes it minus 8. I have another 2 from here, which makes it 10 to the power minus 6. I'm not able to read this. Is 10 to the power minus 6, whatever. So then this becomes 2 into 65 into 12 into 10 to the power minus 6. This is 130 into 12. 12 3s are 36, 12 1s are 12. 1560 into 10 to the power minus 6. That is the position I'm getting, but that's not what they're asking also. I understand that. Okay, let me read the question slowly. Let me approach the sum differently. They have given some third bright fringe from the central maxima for 6000. So 3 into 6500 lambda into capital D by small d, and the small d's value is nothing but lambda into capital D by small d is 2 into 10 to the power minus 3. Let's calculate this value. I don't know what else to do. So then this becomes a 10 to the 6500 and 10 to the power minus 10. It's Armstrong. So this goes up, it will become 2 into 10 to the power minus 3. It goes up, it will become 10 to the power minus 7. So you have a 1.5 into 65. 6000 into 10 to the power 2 is also there. So it's 1.5 into 65 into 10 to the power minus 5. 15 5s are 75. 15 6 are 90. 97.5 into 10 to the power minus 5. That is the position. Again, I don't understand what they are asking here. Seriously, kids, I don't understand. Let me surf the net. I've surfed this. The question is wrong here. The question is only about find the position. So whatever answer we got, see here, this is the right answer. They've given it as 0.156 millimeter. So that's the answer. That is the position at which there's nothing about the third bright. I don't understand what is that third bright fringe. Nothing like that is given. The question in the internet says a beam of light of wavelength 5200 Armstrong, 6500 Armstrong is used in Young's double slit experiment to obtain interference fringes. What is the least distance from the central maximum on the screen where the bright fringes due to both the wavelength coincide? Given that 2 mm is a small d and 120 is a capital D. That's all is the question. I don't understand. They've messed up something here. Please check with your school. That's really taking a lot of time to infer that the question is wrong. And so n is equal to 4 is correct. The fourth and the fifth bright fringe. The fourth for 6500 and the fifth for the 5200. Okay, let's go to next question. Again, sort out the question, guys. Young's double slit experiment. The fringe of 0.1 millimeter. The fringe width itself is 0.1 into 10 to the power minus 3 meters is obtained on the screen using a wavelength lambda is equal to 4000 Armstrong. On replacing the source by 1 of the light by 1 of lambda is equal to 6000. Okay, you're going to change the wavelength to 6000 and moving the screen twice the distance than earlier. So if it was capital D in this case, it's going to be 2D in this. Twice the distance than earlier. Calculate beta dash. Okay, so in the first case, you know, beta itself is lambda into capital D by small d. The second case is beta dash. In this case, it's 4000. In this next case, 6000. Of course, into 10 to the power minus 10. And this also into 10 to the power minus 10. Into capital D will become 2D by small d. That is beta dash. And here, this value itself is 0.1 into 10 to the power minus 3. From this, you can find what is capital D by small d. From the first equation, what is capital D by small d? 0.1 into 10 to the power minus 3 by 4000 into 10 to the power minus 10, which is 0.1 into 10 to the power minus 3 by 4 into 10 to the power minus 7. This goes up, it will become 10 to the power 7. So that and this will become 10 to the power 4. 0.1 into 10 to the power 4 by 4. This is 10 to the power minus 1. So it will become 10 to the power 3 by 4. 1000 by 4 will be 500 by 2. So 250 is what you get for ratio. So you substitute that in capital D by small d here, which makes it 6000. The beta dash will become, therefore 6000 into 10 to the power minus 10 into 2 into 250. This itself is 500. So 6000 into 500 into 10 to the power minus 10. 6 5s are 30 into 10 to the power 5 into 10 to the power minus 10. Okay, 6 5 is 30, 10 to the power 5. This itself is 30 into 10 to the power minus 5. 30, but they seem to be asking a relationship between, the answer is in terms of, okay, what is beta? 0.1 into 10 to the power minus 3. So let's write this in terms of minus 3, which means it's like multiplying by minus 3. You have to get it as minus 3. So 10 to the power minus 2 into 10 to the power minus 3. This one goes here, this one goes here, sorry. Let minus, it will become 0.3 into 10 to the power minus 3. Therefore, you get beta dash is equal to 3 times beta. So that's sorted. So 11th question. In Young's double slit experiment, the distance between the slit D is equal to 0.3 into 10 to the power minus 3. Distance between the screen and the slit capital D is equal to 1 meter. The distance of the fourth bright fringe. So you know that the position is fourth bright fringe, 4 into lambda into capital D by small d. Itself is 8.8 into 10 to the power minus 3 from the central maxima. Find lambda. So then you know 4 into, but lambda itself is 8.8 into 10 to the power minus 3 into 0.3 into 10 to the power minus 3 by 4 into capital D. Just substitute all these values and find lambda. So that's about it. Let's go to 12th question. What is the change in the what change is observed in the interference pattern of Young's double slit if one of the two slits is painted so that it transmits half the light? Okay, you know that the intensity and the slit width are directly proportional. So if you're going to paint half of it, you're going to reduce it to half. Okay, so then the intensity is also going to get halved. What changes after the interference if one of the slits is painted so that it transmits half the light intensity of the other? So you have two slit widths. One is producing half the intensity, while the other one is producing I. One of the slits is painted so that transmits half the intensity of the other. So it's, I'm assuming it's I and I by 2, and you want to find I maximum. So if it's going to be I and I by 2, the ratio of the intensities is I by 2 by I and I get cancelled, is 1 by 2, is the ratio of I1 by I2. That's the ratio of I1 by I2. You know that that's nothing but A square by B square. Therefore, A by B is equal to 1 by root 2. So A is equal to, okay, root 2 A is equal to B, or yeah, root 2 A is equal to B, or A is equal to B by root 2. So now you know what is A and B, and for I maximum, it's A plus B the whole square. But here the A and B itself is like this. A itself is B by root 2, or B itself is root 2A. So we'll keep it like that, root 2A the whole square. That will give you your I maximum, and I minimum is A minus root 2A the whole square. Okay, or you can even write it as A plus B the whole square by A minus B the whole square itself. I maximum by I minimum is A plus B by A minus B the whole square. You can again take B square out common, A by B plus 1 the whole square by A by B minus 1 the whole square. So A by B itself is 1 by root 2 plus 1 the whole square by 1 by root 2 minus 1 the whole square. So it's 1 plus root 2 by 1 minus root 2 the whole square. So if I'm going to expand this, it's 1 plus 2 is 3 plus 2 root 2 by 1 plus 2 is 3 minus 2 root 2. On rationalizing, 3 minus 2 root 2 by 3 minus 2 root 2 is a square minus b square, which is 9 minus 8, so 1. So it's a square minus b square on the top. No, it has to be a square minus b square on the bottom, so that it becomes 1. And that is 3 plus 2 root 2 the whole square, which is 9, plus 2 root 2 the whole square, which is 8, plus 2ab is 3 to 6, 6 to 12 root 2. 17 plus 12 root 2. But they've not asked for the ratio. They ask for ratio, you can do this. But they're asking for I maximum and I minimum. Okay. Separate, they're not asking for the ratio of it. They're also, then we have to proceed it in different way. And I maximum formula is itself I1 plus I2 plus 2 root I1 root I2 into cos phi. That's this is the resultant intensity. It's got to be maximum. Obviously cos phi has to be 0, so that's when you get maximum. So this is what it is, which is nothing but root I1 plus root I2 the whole square, which is nothing but root I1 plus root I2, or in other words a plus b the whole square. Just that you have to find. And you only have the ratios, so how do we find that? So individual intensities கேட்குறாங்கன்னா இந்த ஃபார்முலா தான் தெரியும் எனக்கு, I1 plus I2 plus 2 root I1 I2 cos phi. In that case you know that one has got half the intensity. Okay, for maxima you know that phi has got to be 0. So it pena on this, if the intensities are one is half the other, so I1 is half of I2. கரெக்டா? ஸோ I2 is 2I1 எழுதலாம். ஸோ I1 plus 2I1 அப்படின்னு எழுதலாம். ஓகே, I1 plus I2 plus 2 root I1 I2 can be written as I1 plus 2I1 plus 2 into, this is I1, this is I2, I2 is 2I1, so root of I1 into 2 root I1. Root 2 I2 itself is root 2 I1. So root of 2 into root of I1. So it's I1 plus 2 I1 plus this itself is 2 root 2. 2 root 2 into I1 is what you get. So once you get, this is for, this itself is 3 I1 plus 2 root 2 I1. I1 plus 2 root 2 I1. So I1 can be taken out common. 3 plus 2 root 2. So I1 is, if you know this value calculated, 3 plus 2 into 1.414. 1.414. So you multiply this and add it with 3, you get 5.83 I1. 5.83 I1 is all I get for maximum. What is this? They put 2.951. That's not what I get. Okay, let me continue. And for I minimum, obviously we are sure no, one is half the intensity of the other. So I1 is equal to 1 by 2 of I2, half of I2. So I2 is equal to I1. Yeah, I've written it correctly and I've got the answer like this. So let's do what this is for I maximum, and for I minimum, you know, phi has got to be the formula I1 plus I2 plus 2 root I1 root I2 cos phi, where phi itself will be 90 for minimum. So it will just be I1 plus I2. It will just be I1 plus I2, which is I1 plus 2 I1, which itself is 3 I1. Because phi itself, according to me, for minima it will become 90. No, the phi is minima is occurring at 180 degree. sorry, minima is occurring at 180 degrees. So I1 plus I2 plus 2 root I1 I2 minus 2 root I1 I2 is what you'll get. And again phi is 180, because of that only it became minus. So it's I1 plus 2 I1 minus 2 into root I1, and this itself is root 2 into root of I1. So it's 3 I1 minus 2 root 2 I1. So it's I1 into 3 minus 2 root 2. And if you calculate this value, you'll end up getting 0.1716. Okay, so this was what is my understanding of the question, and but I've not got the answer. If you see, what change is observed if one of the slits is painted so that it transmits half the light intensity of the other? Half the light intensity of the other. I feel what I have done is correct. I don't find any mistake in what I have done. Okay. So there is a question on the internet where if one of the two slits of the Young's double slit experiment is painted over the transmits half the light intensity of the other, then option A, the fringe system would disappear. Option B, the bright fringes would be brighter and the dark fringes would be darker. Option C, the dark fringes would be brighter and the bright fringes would be darker. Option D, bright as well as dark fringes would be darker. The option here, the solution has been given, the dark fringes would be brighter and the bright fringes will become darker if they do that. Okay, so let's see how it is possible. Initially, when both the slits have the same intensity, the bright fringe intensity is 4I2 is equal to 8I1 and the dark fringe is equal to 0. So we see that the bright fringe would be bright with reduced intensity. The bright fringe would be bright with reduced intensity and the dark fringe would have some low intensity. Initially, if both the slits have the same intensity, then the bright fringe intensity is 4I2 is equal to 8I1. I don't understand this statement. 4I2 is equal to 8I1. Yeah, okay, if you I think what they are trying to say is the dark fringe is still left with some intensity. The dark fringe would still be slightly brighter. Well, the bright fringe is appearing darker. I really know what the hell that is. Okay, I really don't know this. Okay, but I hope I've answered this question, but I'm not getting the real exact answer that's mentioned here though. Okay, this the way I'm assuming the sum is I1 is equal to I2 by 2. On assuming like that, this is the answer that I'm getting. Okay, so let's go to 12th question. A monochromatic light of wavelength lambda is equal to 589 nanometer is incident from air on a water surface. From air on a water surface. What are the wavelength, the frequency of this frequency and the speed of the reflected and the refracted light? Okay, the refractive index of water is 1.33. You know, mu is equal to C by lambda. You all should know this formula where mu is the frequency, and if you want to the wavelength, this is mu is equal to C by lambda, with which you can find the frequency in air. Frequency is 3 into 10 to the power 8 by lambda is 589 into 10 to the power minus 9. If you calculate this, you get the frequency, and during refraction the frequency does not change, it's going to remain the same. So thus that you'll get you the frequency. And then speed, once you find the frequency, you want to find the speed of this in water. Okay, and you know refractive index is equal to speed of light in vacuum by speed of light in medium. Here its medium is water. So speed of light in medium is equal to C by mu. So you know C is 3 to 10 to the power 8. By refractive index itself is 1.33, and substituting this you get the speed of the light in the medium. So what are the frequency and speed of the reflected, and this is a reflected, right? Speed of the light in air with respect to its speed of the light, that is just 3 into 10 to the power 8. Okay, so thus you can answer all these questions. Let's go to 14th question. Okay, white light consists of wavelength lambda is equal to 400 nanometer to 700 nanometer. What will be the lambda range if its light goes through water of refractive index 1.33? So then it's going through water, right? Water. Okay. So you know that there's this formula: refractive index is equal to speed of light in vacuum by speed of light in medium, which is nothing but lambda into frequency in vacuum by lambda in the medium into frequency in the medium, where the frequency does not change. So you know that refractive index is equal to wavelength in vacuum by wavelength in the medium. So if you need wavelength in the medium, if you know wavelength in vacuum divided by refractive index, you know that the wavelength starts from 4400 into 10 to the power minus 9 meter, by the refractive index is 1.33. Thus you get the wavelength, that the starting wavelength in the medium. To you can similarly substitute 700 into 10 to the power minus 7 meter by 1.33. that will give you another wavelength range. Thus using both the wavelength, you find one wavelength in medium using the same refractive index. Thus you can find out the range of the wavelength, how the wavelength range is seen when the light is passed into the water. Similarly, they can also ask about the glass. In that case, refractive index of glass is 1.5. Okay, so that's about that question. So next question is, I hope it's recording, let me see. Yeah. So next question is 15th question. 15th question. A screen is placed 2 meters, capital D, 2 meter away from the narrow slit. Find the slit width. The first minimum lies 5 millimeter on either side of the central maximum. So the position Y is 5 millimeter, first minimum, 5 into 10 to the power minus 3 meter, central maximum, when plane wave of 5000 Armstrong is incident on it. So they haven't given the answer for this. Yeah, they have not given the final answer. It's just this from the central maximum, this position is 5 millimeter. Okay. Slit width, you know, all that you know is Y is equal to Y1 is equal to lambda 1 into lambda into capital D by small d. So you know capital D, you know they're asking for slit width small d, therefore is lambda into capital D by Y. So lambda itself is 5000 into 10 to the power minus 10 into capital D itself is 2 by Y itself is 5 into 10 to the power minus 3, which will get you 2 into 10 to the power minus 4 meter or 0.02 centimeter. That will be the slit width. So that completes that question. So next question is next I'm supposed to do 16th question. The light wave of wavelength 5000 Armstrong is diffracted by an aperture of width d is equal to 2 into 10 to the power minus 3 meters. For what distance traveled by the diffracted beam does the spreading greater than the width of the aperture? For what distance traveled by the diffracted beam? So they're asking capital D, for which the spreading greater than the width of the aperture. See, here comes the topic about Fresnel distance. If you all remember, I would have taught you in class what is Fresnel distance. Okay, I hope it's recording. 44, yeah. Fresnel distance is that distance when this position, from the central maxima, the first minima's position from the central maxima is of the same order as the slit width. Or in other words, the position, the capital D, the screen's position should be in such a way that this y and this small d are the same. So you know that y is equal to lambda into capital D by small d, where you're going to replace the capital D as that Fresnel distance, that distance where the screen is placed, ZF, which is first minima's position. So that can also become D because the first minima should be of the same order as the slit width D. So ZF is equal to D square by lambda. And so considering that small d is 2 into 10 to the power minus 3 the whole square by lambda is 5 into 10 to the power minus 7 for the given data, and you get the value this to be 4 into 10 to the power minus 6 by 5 into 10 to the power minus 7. This goes up, it will become 10, it will be 40 by 5, so it will be 8. Oh yeah, so you got it, we got it as 8. What is that micrometer? How is that? I got an answer 8. What is the mistake I've done? 5000 Armstrong. So let me write as 5000 into 10 to the power minus 10. Then recalculate based on that. Let's see if we're getting 4 into 10 to the power minus 6 by 5 into 10 to the power minus 7. This goes up, it will become again. I'm getting the same answer. Shit, I'm getting only 8 to be the Fresnel distance. It's not micrometer, it's just, according to me, it's 8 meters. 2 into 10 to the power minus 3, 5000 Armstrong. I don't think I've made any mistake, and it has to be greater than this. So that for what distance the diffracted beam, thus the spreading is greater than the width of the aperture. If it has to be greater than that, then the capital D has to be greater than this. It should be greater than this distance, so you can write the minimum distance. So it's, according to me, 8 meters. What have they done? 8 micrometer. That's wrong. Okay. So 17th question. A slit of width A is illuminated by a red light of 6500 Armstrong. For what value of A will the first minimum fall at an angle of diffraction 30 degree? First maximum falls at an angle of 30 degree. Okay. As I read the question, I understand it's a question about diffraction, because minimum falls at an angle of 30 degree. Minima condition for diffraction, because there's only one slit which shows it's only diffraction that we have learned. Okay, single slit diffraction is all we have learned, and you know that the condition is A sin theta is equal to n lambda, or D sin theta is equal to n lambda. So to not to get confused, in diffraction they are using A instead of D. So A sin theta is equal to n lambda. And what they are asking, find the value of A, which means n lambda by sin theta is all you need to put, and n is equal to 1 because it's about first minima, into lambda, which is 6500 into 10 to the power minus 10 by sin theta is sin 30. Just substitute that value, and it's 1 by 2, sin 30 is 1 by 2, so you'll end up getting 1.3 micrometers to be the slit width. And the first maximum falls at an angle 30 degree. First maximum's formula, in a diffraction, the maximum's formula is A sin theta is equal to n plus 1, 2n plus 1. Okay, so it's an odd number. You get A sin theta is equal to n lambda, D sin theta is equal to 1, n lambda. And for the maxima, you'll get D sin theta is equal to 2n plus 1 by 2 into lambda. I think so. Okay, I'm just going to try it. Okay, D sin theta. So then therefore D itself is 2n plus 1 by 2 into lambda by A, in other words. So you're going to put the first maxima, so n is equal to 1 you put, will become 3 by 2 into lambda by A, which is lambda by sin theta, sorry, sin theta. Sin theta is 30, 3 by 2 into lambda. Lambda itself is 6500 into 10 to the power minus 10 by sin 30 is 1 by 2, where 2 gets cancelled. It's 0, 6, 5 3s are 15, 6 3s are 18, 19 into 10 to the power minus 10. Yeah, we're getting the answer. Whatever I was guessing is right. So yeah, I'm just guessing the final formula. Yeah, that's right. So it's 1.95 micrometer. Okay. 10 to the power minus 6, so micrometer. So that's fine. So let's go to next question. Next question is also similar sum. Slit of A is illuminated with red light of wavelength 6200 Armstrong. Find the value of A so that the first minimum is formed at 30 degree. So same sum, right? First minimum. This is diffraction. So you all know d sin theta is equal to 1 lambda. So d is equal to 1 lambda by sin theta, which is sin 30. 6200 by sin 30. Sin 30 itself is 1 by 2. So then it's 200 into 10 to the power minus 10, of course. 6 2s are 12. 2 2s are 4. 6 2s are 12. 124. 0 into 10 to the power minus 10. Okay, minus 10, which will be 1.24 micrometers, the same sum. So let's go to assertion and reasoning. I hope it's recording. Yes. So let's go to assertion reasoning. So then assertion reasoning, light wave enters from air like the glass cover. The energy of the light wave changes. Energy of the light wave changes. Chance energy does not change, hence frequency remains same. So assertion itself is false. Okay. Reason, the energy of the wave decreases as a part of light is reflected back into air. Which frequency remains unchanged? Because if frequency remains unchanged, energy will have to remain unchanged. That's all I know. According to me, everything is, both these are false. If you have an option like that, please put it. So let's go to second one, assertion reasoning. Two slits of Young's double slit are illuminated to two different lamps emitting light of same wavelength. Interference pattern is observed. Wavelength. Two different sources. Are they coherent sources? For carrying out interference pattern, you need coherent source. Otherwise, you will not observe interference. Two different wavelength. No. It should be coherent source which has to have constant phase difference or same phase difference. Same phase. It has to have same frequency. Okay, so let me think. As I said, my answer is right. It's false. That's just because they have the same wavelength, it doesn't mean that it should have the same frequency. It should be same phase. That condition is not even met, so false. Two independent sources of light cannot be coherent, as light emitted by the individual atoms when they return to the ground state or not in. Yeah, this is the reason. They'll ask you the reason, and this is the reason why two independent sources of light cannot be coherent, as the light emitted by the individual atoms when they return to the ground state or not in the same phase. Okay, this is the explanation that you have to write. Just remember that. Individual atoms when they return to the ground state or not in the same phase. So this is there an answer where assertion is false and assertion is false? You don't have an option like that. Okay, let's see. Two Young's, first of all, same wavelength but not produce interference, over. Second one, two independent sources of light cannot be coherent. As light emitted by individual atoms. Okay, let me think of that. Okay, once. See, this is the reason that's been given in the internet, that the two independent sources of light cannot be coherent because they cannot emit waves continuously. They cannot emit waves continuously. So that is, if that is the reason, then we can say it's true and that's the right explanation. But here says cannot be coherent as the light by the individual atoms when they return to ground state are not in phase. I don't understand this, but they say that say supposing there are two independent sources, okay, then they will not emit light They cannot emit wave continuously. That is the explanation that's been given. Just remember it and we'll brainstorm it in class, okay? So let's go to next. So the second reason, I don't know whether this reason is correct or not. Two independent sources of light cannot be coherent as. Let me surf the internet once again. Two independent sources of light cannot be coherent as the light emitted by individual atoms when they return to ground state are not in phase.
According to Byju's, two independent sources of light cannot be coherent because they cannot emit wave continuously. The two independent sources of light will not have same phase or constant phase difference between them.
This is because light is emitted by individual atoms when they return to ground state. Two independent sources of light cannot be coherent. This is because light is emitted by individual atoms. Yeah. Okay. When they return to ground state. Oh, when they jump from higher energy to lower energy. High excited state to ground state is when light is getting emitted. Yes. Even the smallest source of light contains billions of atoms. Even the smallest source of light contains billions of atoms, which obviously cannot emit light wave in this same phase. So that is the explanation, okay? So we get a small light, but that's produced by billions of atoms, which has moved from a higher state to a ground state, which obviously cannot emit light in the same phase. Okay, that's what it is. Let's think about this in the class, okay? We can see that the atoms actually, every atom, when they get into ground state, which means the electrons are in the higher excited state and the jumping, they don't jump directly ground state. Some jumps to 3 to 1, 3 to 2, 3 like that. Everything doesn't jump into ground state directly. So during the process, it's not continuous. So that's what it is, okay? Not every atom can, not all the atoms which is responsible for the light is going to jump directly into the ground state, thereby making the waves discontinuous. So that is the explanation. According to me, the reason seems to be true, guys. Interference pattern cannot be observed for two different lamps, from two different lamps of the same wavelength. So I don't know, first one is false and the second one is true. I don't know what to say. So let's go to, because that option is not even there. Third one, in Young's double slit experiment, the light of green, yellow and orange colors are successively used. The fringe width obtained are, okay, is directly proportional to wavelength. The fringe width is directly proportional to wavelength. Whichever has got a greater wavelength will have the greater fringe width. Okay, so the green has a greater wavelength than yellow and then orange. So then the fringe width of green is lesser. Vibgyor, Vibgyor. So red has the longest wavelength, orange has a longer wavelength, so fringe width of orange is larger. So that's about it. Let's go to next question. Reason, the fringe width beta is equal to lambda into capital D by small d. Beta is proportional to lambda. Yeah, that's true. Yeah, that's true. Let's go to next. A small circular disc is placed in the path of the light from the distant source. The center of the shadow appears bright. Small circular disc is placed in the path of the light. Okay, so obviously the light ray will get bent here, and will what is this? It will appear darker. Or it will appear brighter. Okay, we'll see. Let me think. Okay. Yeah, let me tell you. There is a light wave is coming like this. Okay, it is like an obstacle, which means diffraction is going to occur. So the bending of the light ray around the edges of the obstacle and forming a pattern in the geometrical shadow region is what is diffraction. So definitely there will be a bright spot here. Even though if we are expecting a shadow region, we are expecting a bright spot here. So the circular disc placed in the path of the light, center of the shadow appears bright. Yes, true. Because of diffraction. The waves from the distant source waves from the distant source are diffracted by the edge of the disk. These diffracted waves interfere constructively at the center of the shadow and produce a bright fringe. True. And that's a right explanation too. Next question. The two sources of light which continuously emit light waves of same frequency. Am I recording? I hope I'm recording, guys. Yeah. Two sources of light which continuously emit light waves of same frequency or wavelength with zero or constant phase difference between them are called coherent. Same frequency or wavelength, yeah, true, because anything which has same frequency can also have same wavelength. If you calculate mu is equal to c by lambda, fine. But with zero or constant phase difference, yes, that's a must, and therefore it's coherent source, correct. To observe interference of light, two sources must always be coherent. It's both of them are true. So let's go to case study. Okay, let me continue with the case study a little later. Let me have my coffee. 1 second. Sorry, here comes the case study. Where is it? In Young's double slit experiment, is this one? Where is the case study? When two light waves of same frequency having constant phase difference traveling in the same direction superimpose each other, the intensity of the region superposition gets redistributed between maximum at some points and minimum at some points, and this phenomenon is known as interference of light. So learn this interference definition. In Young's double slit experiment, two slits act as a coherent source. Light waves from these two slits form alternative bright and dark fringes. A very simple and practical example is a soap bubble appearing colored when the white light falls on it. This is due to interference of light rays that are reflected from inner and outer surfaces of the soap bubble layer, which is a few microns thick. The light ray reflected from the inner part of the soap layer has traversed larger path length, and that too depends on the wavelength of the component colors of the light. This leads to dispersion of the component colors along with interference. So there's also dispersion along with interference, which is responsible for the regularly repeating patterns of the component colors. Okay. Coming back, let's read this question. In Young's substrate experiment, the distance between the slit and the screen, two slits, small d is equal to 0.2 millimeter. The first question. The distance between the plane of the slit and the screen, capital D, is 4 meter. The wavelength of the light used is 600 nanometer, 600 into 10 to the power minus 9 meter. The distance between the second dark and the fourth bright fringe. That's got nothing to do with the case study. It's just a normal question. The second dark fringe, it's interference, right? Yeah. Second dark fringe and fourth bright fringe. You have to subtract both of this to get the distance between them. The fourth bright fringe is 4 into lambda into capital D by small t, minus second dark fringe is 2n minus 1. 2n minus 1 into by 2 into lambda into capital D by small t. So put n is equal to 2 here, to 3 by 2 into lambda into capital D by small t. So lambda into capital D by small t can be taken out. 4 minus 3 by 2. It is 5 by 2 into lambda into capital D by small t. You know all these values, substitute that and get your answer. 5 by 2 into 600 into 10 to the power minus 9 into capital D by small t, 0.2 millimeter into 10 to the power minus 3 meters. So you should cancel out this and get your answer. So then you can write this as 6000 and this as 2, and this becomes a 3000, and the 10 to the power 3 will make it 10 to the power minus 6, and this 10 to the power minus 3 goes up, it will become 10 to the power minus 3, and 5 4s are 20 by 2. This itself can be answered 10 into 10 to the power minus 3, which is just 10 to the power minus 2. Oh, there's this. What about the 5? Okay, so 5 into 10 to the power minus 2. That's the distance between. What did I do? 5 by 2. 8 minus 5 by 2. 5 by 2 into lambda into. Everything is right. Why am I not getting the answer? Is it correct? The second dark fringe. It's 2n minus 1 by 2 into lambda into capital D. 2 2s are 4. 4 minus 1 is 3 by 2. The fourth bright fringe, 4 into lambda into capital D by small d. Fourth bright. This is between them. Absolutely right. So I'm trying to take lambda into capital D by small d out. 4 minus 3 by 2. It's 8, 5 by 2. It's lambda into capital D by small d. Lambda itself is 600 into 10 to the power minus 9. Capital D is 4 by small d is 0.2 into 10 to the power minus 3 into 5 by 2 is also there. I'm trying to make it 6000 so that I can make it as 2. Okay, so then the 2 and the 4 get cancelled as 2. The 2 and the 2 get cancelled. 6 5s are 30. I'm getting a 6 5s are 30,000 into 10 to the power minus 3 goes up, will become 10 to the power minus 6. So there is a 10 to the power 3 into 10 to the power 4 into 10 to the power minus 6, which is 3 into 10 to the power minus 2, which is 0.03. Appa. Millimeter. What? I thought I've converted everything into meters. Just check, guys. Okay. I think I've done it correctly only. Just check your answer. It shouldn't be millimeters, should be meters, right? Okay, anyway, second question. In Young's double slit experiment, the fringes pattern on the obtained the screen when D is very less. In Young's double slit experiment. Okay, before answering this question, I will tell you another question, okay, which is very important. In an Young's double slit experiment, if it uses a monochromatic light, the shape of the interference fringe formed on the screen will be hyperbola, circle, straight line or parabola. The answer is a straight line. Okay, when a Young's double slit experiment uses a monochromatic light, source of light, then the shape of the interference pattern obtained on the screen will be a straight line. Okay, a hint for this answer. Young's double slit experiment proved beyond a shadow of doubt that light is wave. Okay, the superposition of the light from two slits produces an interference pattern. The light from the single wavelength is referred to as monochromatic. As a result, the interference fringes created on the screen have a straight line shape. If instead of a double slit experiment, a double hole experiment was given, shape would have been parabola. Okay, instead of double slit, if it is double hole experiment, then it would have been a hyperbola, it seems. It would have been a hyperbola. God knows what it is, but it's a very important question. Come, light from a single wavelength is referred to as monochromatic. So in this question they are saying, okay, in the question is about they use monochromatic light. Young's double slit experiment uses monochromatic light which is going to have the same wavelength. As a result, interference fringes created on the screen have a straight line shape. Okay, I still don't understand, but I can tell you to memorize this answer. It has to be, if you use a monochromatic light in Young's double slit experiment, uses the result obtained is a straight line. So when it's at hyperbolic, so then there are different patterns that will be formed. Let's study when it will be hyperbolic. When will the interference pattern in Young's double slit experiment be hyperbolic or parabolic? So here I give you another hint. When the slits are really wider, which means slit width is so much more, okay, small d is greater, then the interference pattern will be hyperbolic. So you understand when they use monochromatic light, when they what are the things that we are learning now? When they use monochromatic light, the fringe shape is a straight line. Okay, God knows why it's a straight line, but it seems to be a straight line. Then if the small d is really wider, then the interference pattern will be hyperbolic. So these are the two factors that you should know. So the shape of the fringe depends on the width of the slit. Okay. And you know that the wavelength of the light is smaller, then the fringes will be narrow. And the shape basically determined by the narrow and wider is not the shape, right? The shape is determined only by the slit width is what is deciding the shape. I hope you understood. So it's either parabolic or it's a straight line. Okay, we can do more questions in that, but I'll come back to you later. But continuing with where we left here, In the Young's double slit experiment, the fringe pattern as seen in the screen when capital D is very less. I thought small d is more is hyperbolic. What about capital D is very less? That I didn't learn. When capital D is very less, what happens to the shape? Let's learn that. So we can say it is still okay. That's still hyperbolic because D is more. Small d is more means capital D is less. Correct? So it's lambda into capital D by small d. So with that into consideration, we can say that it's going to be only hyperbolic. That's the answer. I know, guys. If you can ask your teachers, that's what I can guess. So let's go to third question. The third question is the intensity of the light wave from two coherent sources, I1 by I2, is in the ratio 25 by 9. The ratio of maximum, which is nothing but a square by b square. So a by b is equal to 5 by 3. So the ratio of maximum minimum intensity I max by I minimum is a plus b the whole square by a minus b the whole square, from which ratios only they are asking, so you can take the b square out. So a by b plus 1 the whole square by a by b minus 1 the whole square, where b square cancel. 5 by 3 plus 1 the whole square by 5 by 3 minus 1 the whole square. So when you take LCM, it's 8 by 3 the whole square by 2 by 3 the whole square. So 64 by 4. So answer is 32. So answer is 32. What? 32 by 2. So answer is 16:1. So let's go to next question. The fourth question, the effect of the angular width of the interference fringes in Young's double slit experiment when the screen is moved near to the slit, which means capital D is decreasing. Angular width, fringe width is lambda into capital D by small d. As capital D is decreased, the fringe width will also decrease. Okay, the effect of the angular width of the interference fringes in Young's double slit experiment when the screen moved near to the plane of the slit. So according to me, it okay. Let's because it says angular width. Expected. The word angular width is the key here. They are not asking fringe width. Fringe width and angular width are not the same. We learned something to do with theta 1, theta 2. Remember previously in Young's double slit experiment, where is theta 1 and theta 2 that we did previously? There is a theta 1 and theta 2 comparison. Theta 2 was for diffraction. And theta 1, can you see, for theta 1 is just x by capital D. This is the formula. That's known as angular, angular width in interference pattern. So we should know that. So you should know that and you should substitute it here. Coming back here. Shit, so much I've done. Okay. So theta 1 is equal to x by D. That is the angular width formula. And so what happens is as near to the, as you move it nearer to it, D is decreasing, which is only going to increase. Okay, so the angular width, you can say, according to me, it's only going to increase. Either way, even if you had put lambda into capital D by small d for fringe with beta, you still get the same answer. So according to me, it's just increasing. 1 second, hold on. The angular fringe width in Young's double slit experiment. Any additional information is what I'm searching for. The fringe width depends on the wavelength of light. Yeah. I want more about angular fringe width is directly proportional to wavelength again and inversely proportional distance. Yes. So it is not going to vary our answer. So the answer remains the same. So that's about it. But you should use this formula. You can't use lambda because it says angular width. Okay. So in fifth question, in the Young's double slit experiment, the path difference is lambda by 2 between S1P SS2, okay, what is nothing but S1P and S2P. S2P minus S1P must be, the path difference is lambda by 2. The condition for the PD to get second bright fringe on the screen. second bright fringe. The question is about second bright fringe. The condition, if the path difference between S is lambda by 2, path difference between them is lambda by 2. It's such a superb question. The path difference formula, you remember in the process of deriving, we would have got path difference S2P minus S1P, which is, we'll name it as delta X. And while doing Young's double slit experiment, we'll get it as S2P minus S1P. You will get 2D is equal to 2D into S2P minus S1P to be equal to y minus d by 2. So you get a 2y capital, 2y small d. Yeah, I remember that. 2 and 2 get cancelled. So S2P minus S1P is the path difference, is equal to y into small d by capital D. Okay, which is the position into small d by capital D. This is the formula for the path difference that we get. And small d by capital D. I'm just trying to think any other way in which I can. So let me try to do this. You know, path difference formula is this delta x into y into small d by capital D, which itself is lambda by 2 has been given. Write this equation. And it's about getting a second bright fringe. A second bright fringe formula is second bright fringe. For the second bright fringe, the path difference itself will be 2 into lambda. Yeah, that's what it is. It's just n lambda. Path difference itself, you remember in the derivation I would have written it as n lambda is the path difference condition. So we'll equate this and this generally. Yeah, and we get lambda into capital D by small d, yn is equal to n into lambda. That's what we do for bright fringe, and we'll equate it to 2n minus 1 by 2 into lambda in the case of bright fringe. So I'm just trying to equate this and this. So then therefore when comparing, you get a lambda by 2 is equal to n lambda. Lambda get cancelled, n is equal to half. N is equal to half. I'm getting a n is equal to half. Do you have such an answer here? The condition for we need to get the second bright fringe on the screen. N has to be 2, right? Second bright fringe. So then therefore you can write this as second bright fringe, which is 2 lambda. So lambda by 2 is equal to delta x itself is n lambda, which is 2 lambda here for this second bright fringe, correct? For the second bright fringe is 2 lambda. So I'm just trying to think what I can do. The path difference itself is lambda by 2. The path difference itself is that is where I could have done. Have they given it's lambda by 2 the path difference? Yes, they have given the path difference is lambda by 2. Very clearly they've given the path difference to be lambda by 2. The condition for getting the second bright fringe on the screen. If the question was about getting a dark fringe on the screen, then I can equate 2n minus 1 by 2 into lambda can be equated to lambda by 2, where lambda get cancelled, 2 and 2 get cancelled, 2n minus 1 is equal to 1, 2n is equal to 2n is equal to, so n is equal to 1. You'll get a proper number. If the question was about a dark, but the question is about the bright fringe, when I'm not even able to equate this and this, because you get 2 lambda is equal to lambda by 2 and the path difference is lambda by 2. Equate this and this, You get 2 is equal to half, which is not mathematically possible. What are they even asking is my question. Young's the path difference between lambda by 2, the condition for you to get the second bright fringe on the screen. Okay, second bright fringe. The formula for second bright fringe, let me write it, is 2 into lambda into capital D by small d, correct? And capital D, lambda into capital D. You know, y into small d by capital D itself is lambda by 2. I'm trying to do something here. Okay, so that's my path difference. So y itself is lambda into capital D. Sorry guys, I'm wasting your time. Once again, let me put it in. Yeah, I think I can recall. In the derivation, I did path difference, and the path difference was y into small d by capital D was equated to n lambda for the bright fringe. And for a dark fringe, I got it as y into small d by capital D is equal to 2n minus 1 by 2 into lambda. This is the condition that I got for the dark fringe. Yeah, and how did I arrive at this? To arrive at that, what did I consider to get n lambda? Lambda is the path difference for phase difference of 2 pi. What will be the phase difference for the path difference being delta x? And I got lambda into 5 by 2 pi. Okay, and instead of pi, I continue to substitute phi to be 2n pi for maximas, correct? I continue to substitute 2n pi in the place of maximas. 2n pi, which shows that, which means I've taken lambda to be the path difference, but here it happens to be lambda by 2. So my the condition for the maxima itself would change. It will not be n lambda according to me. So you will end up getting a lambda by 2, which is 2n minus 1 by 2. N is equal to, you put 1, you get 1 by 2 into lambda into capital D by small d. I think that should be the answer for this, because the path difference is already lambda by 2. They have given that the path difference between this is lambda by 2. The condition for that, because I considered the path difference in that case in the Young's double slit experiment to be n lambda, because that's when I get my maximum. But first of all, if it's lambda by 2, I really don't know. This is something that I need to discuss with you. The fifth sum, you can talk to me in the class, guys. I'm really a little confused about this fifth sum. You can see the answer key and guide me through, but there is a doubt there. Normally bright fringe means it's n lambda, or so you want, it can be 1 lambda or 2 lambda or 3 lambda and so on. But here, because the original path difference itself is lambda by 2, for a lambda by 2 which will occur for a phase difference of pi, which means only a minima can occur there, but we are talking about a maxima. So I'm slightly confused about this sum. Okay, so sorry, I have taken too long to think about that and say no, I don't know. So let's go to first question, the next paper, MCQ. In the Young's double slit experiment, the separation between the slit is halved. The d is becoming d by 2, and the distance between the slit and screen is doubled. The capital D is becoming 2d. The fringe width, the original fringe width is lambda into capital D by small d. Beta dash is lambda into 2d by a d by 2, so it's becoming 4 times. So let's go to second sum. The force sustained interference of light. The necessary far sustained interference of light. The necessary condition is that the two sources should be coherent. For sustained interference, should have a constant phase difference. That's what is coherent sources. So therefore it is A. The two sources should be narrow, should be close to each other, should have the same amplitude. So now I'm going to tell you the conditions for sustained interference, the condition required for the sustained interference. Okay, so the two sources of light must be coherent, which you already know. They should be at the same phase or with constant phase difference. The two sources must emit light of the same wavelength, but the amplitudes between them should differ as little as possible. Remember, we took it as small a and small b. The amplitudes are slightly different, but they have the same wavelength. The two sources must emit light of the same wavelength, but should have slightly different amplitudes. Okay, such as small a and small b. The emitted waves should be preferably of the same amplitude to get completely dark fringes. If you want completely dark fringes, then they should have same amplitude. But it can have, for sustained interference, it should have slightly different amplitudes. Okay, the two, forget about the same wave amplitude, same amplitude part, because we don't talk about it at all. We just take it as A and B, and we simply say it's completely dark and bright anyway. The two sources should be very narrow. Otherwise, with the increase in the slit width, the coherence property will be lost. Hence, no interference pattern will be obtained. So that's the reason you have to have a slit width which is very, very narrow, and should be of the order of the incident wavelength, or the incident wavelength should be of the same order of the slit. The two sources must lie as close as possible to each other. Otherwise, overlapping of the bright and dark points will hinder interference. Overlapping of the bright and the dark points will hinder the interference. At maxima, the path difference between the two light waves is always an even multiple of lambda by 2 at maxima, and it is odd multiple of lambda, and at minima it's an odd multiple of lambda by 2, an even multiple of lambda by 2. So 2 lambda by 2 is 1 lambda, so it makes sense. So these are the conditions for sustained interference. So considering all these conditions, which one will go for it? Slit should be narrow, constant phase difference, close to each other. Have same amplitude. No, should have slightly different amplitude. So the necessary condition is that the two sources should be, everything is there other than D. I don't know what to say. Okay, I really don't know. Everything is so important for sustained interference. The phase difference between any 2 points on the plane wavefront is obviously be 0, right? So the phase difference between any 2 points on the plane wavefront is 0. So that's the answer for the third question. See, because wavefront itself is the locus of the point which are vibrating in the same phase, so there should be no phase difference. A type of wavefront produced far away from the point source will be spherical wavefront. When the wave traveling from the rarer medium gets refracted into a denser medium, a rarer medium gets refracted in denser medium, the speed of light decreases, the wavelength, speed of light decreases, ray bends away from the normal. Okay, so let's see, when the wave traveling from rarer medium gets refracted into a denser medium, so what happens to its wavelength? Wavelength decreases. So option A is not possible. Speed of light increases, it decreases, so that's also not possible. Ray bends away from the normal. What? No, the frequency of light remains the same. So option D is right answer. Let's go to the next question. Sixth question. The wavelength of the incident light on the denser medium of refractive index mu is equal to 1.5. The wavelength itself is 400 nanometer. The wavelength of the light inside the denser medium. The wavelength of the light on the denser medium is the wavelength of the light inside the denser medium. What is the first line? The wavelength of the incident light on denser medium of refractive index is, okay, this is incident light wavelength. What happens to the wavelength in the denser medium? You know that refractive index is wavelength in vacuum by wavelength in the medium. So wavelength in the medium is equal to wavelength in vacuum by the refractive index. So do that and you get the answer. So let's go to what is given as the wavelength in vacuum, obviously. So substitute that and you mark your answer. Let's go to 7th question. The distance between the plane of the slit and the screen is increased, then the angular width of the fringe. Angular width, as I said, is that you just saw it, theta 1 is equal to x by capital D. If the distance between the plane and the slit and the screen is increased, the angular width of the fringes is going to decrease according to me. You just tell me if it's wrong. So 8th question. A soap bubble appears colored when the light falls on it due to both scattering of the light and also due to we had a case study, right? So 8th question, a soap bubble, okay, அது முன்னாடி இதை பார்க்கலாம் பாரு, அந்த இதுலேயே கொடுத்துருக்காங்க பாரு. The light ray reflected from the inner part of the soap layer has to traverse larger path length and that too depends on the wavelength of the phone. 1 second. இப்படி தான் விட்டு விட்டு பண்ணியிருக்கேன் ஃபுல்லும், ப்ரொஃபஷ்னலாக இல்லை வீடியோ. பட் எனிவே இன்டர்ஃபரன்ஸும் காரணம். அணையா ஃபோனை அணையா, இன்டர்ஃபரன்ஸும் காரணம், அதுக்கப்புறம் இதுவும் காரணம். எது? ஸ்கேட்டரிங் ஆஃப் த லைட். ரெண்டு ஃபினாமினும் சேர்ந்து தான் யூ கிவிங் ரைஸ் டு ரெயின்போன்னு படித்தோம். அதையே எடுத்து இங்கே காப்பி அடிச்சு விட்ரு. ஸோ அதையே எடுத்து இங்கே காப்பி அடிச்சு விட்ரு. கட் பண்ண மாட்டேங்கிறாடா லைனை, எப்படி கட் பண்ணணும்னு தெரில எனக்கு. சில பேர்லாம் அப்படி தான் எதாவது பண்ண வேண்டியது வரக்கூடிய. ஓகே, நான் என்ன பண்ணியிருந்தேன்? ஸோ பிகாஸ் ஆஃப் இன்டர்ஃபரன்ஸு, ஸ்கேட்டரிங் ஆஃப் லைட் இருக்குது. அப்போ நான் எதை மார்க் பண்ணுறது? soap bubble appears colored when light ray falls on it due to falling on it is due to interference தான் போடணும். இதை பொறுத்த வரைக்கும் டைஃப்ராக்ஷன் போலரைசேஷன் கிடையாது. பட் ஸ்கேட்டரிங் ஆஃப் த லைட் ray is happening, white light falls on it due to scattering of the light layயும் பாசிபிள் ஆச்சே. ஸோ நான் என்ன போடுவேன்னு தெரியலையே. இங்கே திருப்பியும் போ, அந்த பேராகிராஃப்க்கு போ, திருப்பியும் போயிட்டு அந்த ரேயை படி. Hey, wait guys, they're going on calling me stupid young double static. The light ray reflected from the inner part of the soap layer has to traverse a larger path. Okay, this is due to interference. A very simple practical example: soap bubble appears colored when the light falls on it. This is due to interference of light ray. They are reflected from inner and outer surface of the soap bubble layer, which is few microns thick. Inner layer and outer layer, light is getting reflected by the inner layer as well as outer layer due to interference of the light ray. The light ray reflected from the inner part of the soap bubble has to travel a larger path, and that too depends on the wavelength of the component colors of the light ray. This leads to the dispersion of the component colors, along with the interference. So scattering of the light along with interference, which is responsible for regularly repeated patterns. For the repeated patterns, interference is responsible. Now we are clear. For the repeated patterns, interference is responsible, but otherwise scattering only is responsible. So I would write scattering of light. If you disagree with me, you can argue with me in the class. 9th question, a point source that emits waves uniformly in all directions produces spherical wavefront. Okay, next the shape of the reflected wavefront obtained through the concave mirror will be convergent. Concave mirror will be convergent. Okay, so then if provided it's a parallel beam of light, will become convergent. Yeah, plane wavefront will become convergent. So that completes one set of paper PS senior.